These are the notes on Unit 5 of Chapter 1. This is on negation of statements. So, very general idea what a negation is. Negation of P just means that not P. So if you have P and you want to negate it, just say not P. There's a few ways to express this mathematically. The two most common forms of negating something is the statement followed by like a little apostrophe or like a tilde preceding the statement. Both of these mean not P. Just different ways of expressing it. Then there's a few more complicated things that can negate other than just a single statement. First off, you can negate a conjunction, so you have P and Q. If you wanted to negate that, that's what the little apostrophe is, negation. You can make that not P and not Q. And if you want to make that in a way that makes sense visually, you can create like Venn diagram, P and Q. So first, not P and not Q, well, we would know this already to mean because anything that's not inside the little intersection point. But if we approach it this way, you can say, alright, highlight everything that is not in P. So we'd highlight all of Q over here, and we'd highlight all the stuff out. And then, or, oh wait, that should be an or, sorry about that. Or anything that's not in Q, so that we can go and highlight everything that's not in Q, so we go back, highlight all that stuff again. Also, this stuff in P is not in Q, which gives us back to the same results of everything just not in that intersection of P and Q. Then you have the disjunction. P or Q. Way this works, it's kind of like how the previous one works, where you distribute the negation down and flip the center sign, so it becomes not P and not Q. So then do the same thing again. We can find, I'll use blue for P and, blue for not P and red for not Q. Oh yeah, I'll label these. Sorry, going too fast for my own good. Alright, so everything not in P. Let me put this circle some blue. Well, let's see. None of this outside stuff is in P, so we can get all that circled. And nothing in Q is in P as well. Then, not in Q, so again, all this outside stuff is highlighted, and all this stuff over here in P but not in Q gets highlighted. And since we're trying to find and, we're trying to find the spot where they're both statements hold up, which is everything on the outside. So then if I redraw this in a way that makes it a bit more clean, we'll say not P and not Q, just all this stuff outside of the sets of P and Q. After you have this, then you have to you have to negate conditional statements as well, because like if P then Q, but what happens if P then Q is not a true statement? You want to negate it. So you have P then Q and to this. So This one is slightly less intuitive, but if we go back to the chart from the previous one, we could say that we used in the previous unit. We have if P is true and Q is true, then P then Q is true. If P is true and Q is false, then P then true is false. If P is false and Q is true, this one was a tricky one, remember, but this one is still true. And P is false, Q is false, this would be true. So if we negate this, we can say that the negation of P then Q would have to be false, true, false, false. And see, it's only true when P is true and Q is false. Notice the emphasis on the word and, which kind of leads us to next step where this equals P is true and Q is false, or not Q. It makes a little bit more sense when you start looking at the graph, but it's still understandable if you can't intuitively understand that. After that, you get into definitely more complicated stuff. You could say this is going to be a very common thing for some A, or for some, I guess you say for some P, Q happens, which is for some, that's a terrible backwards E. For some P, such that for some P such that Q happens. This statement, this could also be really big. For some integer x, x plus 1 is greater than x squared, anything like that. Because, well, that statement is true for some of them, 0 and 1. But it can be this simple. And the opposite of it isn't that for some P, Q doesn't happen, because that's actually implied by the statement. But instead it's for all P, Q does not happen. Which we would write for all P not Q. That could also be something really big, like if just a really big mathematical statement, but this right here, this is pretty easy to work with in my opinion. Let's see, and then the other one, for all P Q happens. So if we start off, for all P Q happens, you can negate this kind of the same way that was done on the previous one, where we switch from for some to for all. Do that backwards, and where we then proceeded to switch this to a negation. There, for some P such that Q doesn't happen, or in a more Englishy way, there are some P where Q does not happen, which is obviously, if you say all cars are green, well, you can say some cars are not green, which is applying this principle right here. You can go into really complicated mathematical expressions with these, but this is really just the gist of it all at the basic level. And after that, I think that's pretty much all of the notes for this unit. So, bye.